So welcome everybody. I'm happy that we are all here and that we can welcome Kevin Heng to give the seminar today. So I just briefly introduce him. Kevin Heng grew up in Singapore, where he also started his studies, then went to Colorado at Boulder, where he also received his PhD in 2007 in astrophysics. Afterwards, he went to the Institute for Advanced Studies at Princeton, and where he was a Frank and Peggy Taplin member and also member of the Institute. Later on, he went to ETH Zurich, exactly as a postdoc. And then he went to the University of Bern, where he became professor in 2015. And since 2016, he is the director for the Center for Space and Habitability at the University of Bern, where he is also serving today. He is also an honorary professor at the University of Warwick, starting this year to 2022, and he received numerous awards and grants, including, for example, the ERC Consolidated Grants for the project Exoplanets. He's a member of several missions like TESS, SANT-X, Cheops, Plato, just to name some of them. And he is also known for his graduate level textbook that he published that is called Exoplanetary Atmospheres, Theoretical Concepts and Foundations. So we are very happy to have him here today to give a seminar. So the screen is yours, Kevin.
Caro, thank you very much, all of you, for the invitation, and Caro for your very kind introduction. So hopefully this works smoothly. And it still works smoothly. That's good. Okay, great. So I'm really not just talking about my individual work. I'm talking about the work of a collection of people that I have the fortune to collaborate with, 4 PhD students and 6 postdocs in my group currently. And it's not possible to tell you about all of the work that we are doing. So a part of the group does, we do 3D fluid simulations, so general circulation models. That's a part of the group that's interested in atmospheric chemistry. I spend a lot of time thinking about radiative transfer. And in recent years, I've been pulled more and more, sometimes reluctantly, into the direction of Bayesian inversion methods. Actually, first with Caro's work, I was put in that direction because I realized that you have to learn that to analyze data. So today I'm going to attempt to give you some flavor of what we are doing. Not all of it. I'll focus mostly on the radiative transfer and the Bayesian inversion methods part. And then if there's time, the last third of the talk, I will tell you about 3 big questions that I think are exciting in the next 5 to 10 years in my field. This talk was previously given at a different university, and it was given to a broad audience of physicists. So this is the tone I will try to strike. And if there's anything that's not clear, please interrupt me. So let's start with asking the question, why are the atmospheres of exoplanets interesting? And I would say, I don't need to tell you that the most basic properties of an exoplanet are mass and radius, but this only tells you so much. For nearby objects, you actually can record spectra of exoplanetary atmospheres. And depending on what type of planet you are, these spectra give you constraints on atmospheric chemistry, and they either tell you something about the formation history, or they tell you something about the habitability conditions, which I will elaborate more as we go along. And one of the reasons why atmospheres is interesting and important and a priority in astrophysics, as you can see in the investments made by NASA and ESA, is that the hunt for extraterrestrial life must proceed via the detection of biosignature gases from atmospheres. Unless you master interstellar travel, this is the only option. And whether a gas is a robust signature or not depends very strongly on the atmosphere it's embedded in. I'll give you one toy example of that we can all think about. So to start with a cartoon, this is every exoplanet scientist's dream. You think of this TRAPPIST-1 dreamscape. And then you think of landing a rover on it, like you land a rover on Mars and you dig a sample and you bring it back to Earth and then you analyze it and everyone is happy. And unfortunately, this is not the reality. The reality looks more like this. So because these objects are so far away, the reality is that besides mass and radius, your only access to more chemical information about the exoplanet is through its spectra, whether emission or transmission spectra. And then you have to do the tedious and maybe boring but important work of, given a measured spectrum, you would like to solve the inverse problem, and you would like to say what the chemical abundances are. But you would like to do it in a way that takes into account all of the different degeneracies in the model and the uncertainties of your measurement. And this is a big theme of the talk today. So the agenda today is I'm going to give you some motivation. Then I'm going to talk about interpreting spectra using traditional Bayesian methods, and then using machine learning. I'm going to argue why machine learning adds value and is not just being used as a trendy black box. And if there's time, I'll talk about big picture questions for the future. So the state of the art currently is that there are two methods. There are workhorses. This is the radial velocity method and the transit method. I don't need to belabor these points. And it's probably not surprising that you can get spectra of atmospheres from transits, but maybe it's perhaps more surprising that you get for free from radial velocity data also spectra of atmospheres, which I will tell you about shortly. And once you have these spectra, for gas giants, you would like the atmospheric chemistry to tell you something about the formation history. And for rocky terrestrial exoplanets, you would like to say something about biosignatures. This is still an aspiration. We're really not there yet. And I would like to show you a few examples of what I mean. So the current state of the art is there's an instrument on the Hubble Space Telescope called the Wide Field Camera 3, WFC3. And WFC3 is designed so that it records a 1.4 micron water feature. And the community took a lot of twists and turns before finally converging on a data reduction and an analysis method that actually gives you robust results from WFC3. There's a whole chain of papers in this. Here's one very good example. And as of today, there are more than 40 transmission spectra that have been measured, mostly from hot Jupiters, so more than the solar system so far. But the problem is that this, well, it's not a problem, but the limitation is that this kind of observation is expensive, difficult to do, but limited. It mostly tells you about water, and it tells you a little bit about ammonia and methane, but these statements in the literature are mostly model dependent. And some people believe that it tells you about hydrogen cyanide, but it mostly tells you about water. And when the James Webb launches, hopefully next October, this will change dramatically because of the wavelength coverage and also the spectral resolution. I'll talk more about this in the machine learning part. The other nice thing about the recent data is that you can also record flux as a function of phase, just like you're seeing phases of the moon. So if you really understand your instrument and you can get exquisite photometry, like say with the Spitzer Space Telescope, then you have a chance of resolving the modulation of flux as a tidally locked planet shows different phases to you across orbital phase. And I'm sorry, and this on the left, the figure on the left shows you this paper that really, this was really the 2007 paper that made me drop my PhD topic and change to this topic, because I thought that Heather Knutson's observations of this hot Jupiter was so awe-inspiring that I thought I needed to study this. In between, there were many phase curves. Another phase curve that is quite well known is of this famous object. These are the two most studied hot Jupiters in history. And one of the exciting things about Webb is that now you can get multi-wavelength phase curves. So you can get not just information across wavelength, you can get information across phase as well. And one of the very exciting techniques that one of my postdocs, Jan Humakers, who came to me from Leiden, he just left to be a professor at Lund, is this method called cross correlation. So if you, I'll talk much more about this, But in a nutshell, basically you can measure spectra from both the star and the planet. And the power of this method is not just that you measure the spectra, but you measure the spectra across time as the planet orbits around the star. So that as the planet orbits around the star, the spectral lines in the atmosphere of the planet shift back and forth. They get blue and red shifted back and forth. And this actually then allows you to extract the signal of the planet from the signal of the star. And once you get the signal of the planet, you can actually cross-correlate the rather noisy spectrum with cross-sections of atoms and molecules. And then you can say very robustly if these atoms and molecules are actually present in the atmosphere in a largely model-independent way. Because the only thing that you put your faith in is that quantum mechanics is correct and that you're getting the correct cross-sections of atoms and molecules. As I will show you later in the talk, it's much harder to say how much of each atom and molecule is there and what the temperature is and so on. But it's relatively easy to say if a given molecule is there, yes or no. This is a very robust question you can answer. The disadvantage, which I will tell you later in the talk as well, is that when you measure these spectra from the ground, you do not have an absolute normalization of the spectra because you have to subtract the influence of the Earth's atmosphere. And this translates into getting relative and not as absolute abundances. So I'll summarize this for you later in the talk. Here's one example of this method at work by Jens Humakers, whom I mentioned, who is now just moved to Sweden to be a professor. And he focused on the lines of iron plus in this object called Kelt 9b. And what you see here is you see, this is x-axis is velocity, y velocity is time, y-axis is time, sorry. And as the planet moves across the orbit, you see the lines of iron plus, dozens of lines, not just one line, go from being blue shifted to being red shifted. And now when you add up this signal across the orbit, you actually get a rather significant signal. And if you fit a Gaussian to this signal relative to the noise level, you get a ridiculous amount of sigmas of this detection. So it's a very, very robust detection of iron. And this paper actually reports the first robust detections of iron and titanium in any exoplanet atmosphere. And there's a subsequent paper where Jens took a second data set of this planet and cross-correlated through the entire periodic table. And he was able to report detections of chromium and scandium and yttrium, rare earth metals as well. So my opinion is that this is probably the most robust method. If I was to believe the claim of biosignatures coming from anyone, it would be from this method. But unfortunately, my understanding is that the number of objects, Earth-like exoplanets currently known for which you can do this kind of analysis, you can count on one hand, I believe. So to end this section, I asked myself the question, how does one make impact? It's very clear that there are lots of exciting things happening in the observational realm. This is a observational, exoplanet science is a field led by observations. The theorists are always trailing behind. But you can make impact by thinking about state-of-the-art data interpretation methods, including traditional Bayesian and machine learning methods, which I will talk about today. And you can make impact by thinking carefully about the theoretical foundations of exoplanet atmospheres, because we can learn a lot of lessons from the planetary and earth sciences, but you cannot translate this information blindly without thinking about it. So now to move on to the proper talk, I would like to talk to you about transmission spectra. So this is the typical setup of how you would do this kind of analysis. You have a spectrum, a transmission spectrum in this case. I forgot to say, a transmission spectrum is when a planet passes in front of the star and you detect variations in the projected size of the planet because of variations in how opaque or transparent a molecule is. So this comes directly from the cross section. So for example, when you look at 1.4 microns and the planet is the planet's atmosphere has water, and water is more opaque at 1.4 microns, you will register a slightly bigger size for the planet. And now if you move away from the 1.4 micron feature, the size will shrink a little bit. And this measurement was very hard to make because this is at most 1 part in 1,000. This is a very small effect. And it took a long time for people to trust this kind of measurement. But given the measurement, then you would like to have a forward model that converts your opacities, which are cross sections per unit mass, and some kind of chemistry model, if you have one, into a synthetic spectrum. You would like to think carefully about what are your prior beliefs on your parameters. And you would like to then scan parameter space using an MCMC, for example, to figure out what the posterior distributions of these parameters are. And if you can calculate something called the Bayesian evidence, you would like to identify the simplest model, not too simple, but the simplest model that is consistent with the data, that does not need additional complexity. So this is a application of Occam's razor. And one of the rules that I always tell my research group members with retrieval is that you should remember the rule garbage in, garbage out. These tools are not black boxes. So if you put in garbage, you will get out garbage. So it doesn't mean that just because we have these state-of-the-art tools, you don't need to pay attention to the physics. So you need to pay real attention to the physics. And one of the things that was quite subtle that we paid attention to is something called the normalisation degeneracy, which I'll now describe to you. So shown on this plot is a transmission spectrum again, is basically the relative size of the planet as a function of wavelength. And which data set this is not so important. The point of showing this data is to show you give you a feeling for the size of the error bar, and then to give you a feeling of the variation in the model curves relative to the size of the error bar. In this paper, this author has plotted 4 models, and it turns out that the theoretical normalization of the model cannot be calculated from first principles. So she has chosen 4 normalizations to try to fit this data. And you can see the variation in the normalizations is very small, right? It's in the second decimal place. But this seemingly tiny variation in the normalization of this reference radius leads to a variation of the water abundance across 5 orders of magnitude. And this was noticed also numerically by Banneker and Seeger, but no theoretical explanation was properly given. But this is a real problem if you want to extract abundances. So in 2017, we thought about this problem, and we published the explanation for this problem. Now, if you make certain assumptions, which I don't have time to go through, if you assume that this transit chord across the planet's atmosphere is isothermal, then you can derive a closed form expression for the transit radius. So the transit radius observed by the telescope at some wavelength is some reference radius multiplied by a characteristic length called the pressure scale height, which is typically 1% of the radius of the planet, and a bunch of stuff. There's a factor of a few, right? And the bunch of stuff includes boring things like some constant, the gravity of the planet. But this is not boring. This is the part that you're really interested in. This is the opacity of the combined opacity of all of the atoms and molecules in the atmosphere. And the opacity also includes the abundances. So this is the quantity that you are interested in. Unfortunately, the reason why it's really hard to extract this quantity is because of this three-way degeneracy. So there's a reference radius, and there's a reference pressure that corresponds to a reference radius. And then there's the opacity, right? And the opacity contains the abundances of water that you're interested in. But you can see that because these two quantities are multiplied together, there's a degeneracy. And also because you cannot specify this, you cannot easily specify this relationship between the reference radius and the reference pressure, because you need to know uniquely the interior structure of the planet, which you do not know. So because you do not know this relationship, you need to set them as 2 independent numbers. And therefore, a tiny shift in this number needs to be compensated by a gigantic shift in this combination of numbers. This is the reason why a tiny shift in the reference radius leads to a huge variation in the chemical abundances. And there was no name given to this. I call it the normalization degeneracy. The proper solution to this is that when you fit these spectra, you need to pick a value for one of these quantities, and you need to fit for the other one. So in the following, when I show you spectra, we are going to set this reference radius to the measured radius of the planet. Then we're going to fit for the reference pressure. So one example of such a fit is this. So this is the reference pressure. And now this in red is the Hubble with C3 transmission spectrum of some hot Jupiter. It's not important. In blue is the model, and in black is the bin data points of the model. And this simple model has just one temperature, the abundance of water, the abundance of clouds in the atmosphere, and this normalization. And what is important is that, yes, these posteriors look bounded, but for different reasons. The right side of the posterior of water is bounded by the fact that if you get too water rich, your pressure scale height in the atmosphere gets too small, gets smaller and smaller because you get metal rich. And then you need more and more scale heights to explain this feature. So if you make it too water rich, you run out of scale heights to actually explain this feature, which is why you get this trailing off. But the trailing off on the left is not real. The trailing off on the left comes about because you have hit the prior of the normalization factor P naught. So we have chosen, because we don't know what this should be, we have chosen the right side of this prior to be 1,000 bars, 1,000 times the atmospheric pressure of the surface pressure of Earth. And this edge here corresponds to this edge here. So it's prior dominated on the left side. The other thing about this analysis I wanted to describe is that you do not just fit one model to the data, you fit a whole family of models. And you have a model, and the model I'm showing you is the best fit model. It has one temperature, one molecule, and it has a so-called gray cloud described by one number. You can also have 3 molecules and a gray cloud. You can have a non-gray cloud. You can have a non-isothermal atmosphere. You get the idea. So you fit the whole families of models to the data. And the ones in green are all consistent with the data. The ones in blue are weakly disfavored. And the one in red is moderately disfavored, which is good to hear because the one in red is a flat line. So this is inconsistent with a flat line. Not all of the transmission spectra are. So this is a closer look. I'm sorry, I should have flipped to this slide sooner, but this is a closer look at all of these models and their so-called base factors. And if you want to learn about base factors, there's this wonderful review by Roberto Trotta, who is a cosmologist, I believe. This is a beautiful review that not only talks about the philosophy of Bayesian inference, but tries to draw a correspondence between the frequentist way of thinking and the Bayesian way of thinking. So if you're interested in this, I highly encourage you to look at this review. So at the end of this analysis, what we get out are water abundances. And then we try to put them on a plot with, say, some property of the planet, like the mass, and we hope that this tells us something about planet formation. Unfortunately, with the Hubble data, you don't really see that much. You cannot really say that much because of the difficulties I described to you with the normalization degeneracy. So my eyes don't see a correlation. Maybe yours do. So I would say that the use of chemical abundances retrieved from the atmospheres of gas giants to constrain meaningful things about planet formation remains an aspiration for now, but not for long, because when Webb launches, one thing I didn't show is that the Webb spectra has enough wavelength coverage and resolution that you can actually break the normalization degeneracy. There's actually enough information in the spectrum to do that. And with the Webb spectra, you can get much more robust chemical abundances, not just of water, but of all of the major carbon, oxygen, and nitrogen carriers. So my opinion, which may not be shared by everyone, is that the Webb spectra will revolutionize this path of research in the very near future. I'm happy to take questions at this point because I'm going to go to a different segment of the talk now. If not, I'll keep going. So the next question we wanted to ask is, how may we go beyond the traditional Bayesian approach? And one of the things that was really on my mind was the fact that when you run, say, a model in an MCMC or nested sampling, you have to compromise between how realistic you want your physics and chemistry to be, but you cannot go overboard because the model has to be simplified enough that you can run 1 million models in a few minutes or something like that, so that you can actually finish the inference to gain some physical intuition. So there was always a tension between physical realism and computational feasibility when you use these traditional Bayesian retrieval methods that I just talked about. So we started asking this question: how can we do things differently? And to understand this, you have to go back to Bayes' theorem. Bayes' theorem is the relationship between the posterior, the prior, the likelihood, and the evidence. So the posterior is what you're interested in. This is the probability distribution of, say, molecular abundances and temperature and cloud properties given the data. You have to pay attention to what your prior beliefs are, as I already told you. So the normalisation degeneracy is a type of prior belief that turns out to be important. The evidence, as I quickly described to you, is a way to implement Occam's razor. But the most interesting thing in this relationship is the likelihood. So what actually is the likelihood? The likelihood is not a probability distribution. The likelihood is a mathematical relationship between the data, the model, and the noise. And at least in my corner of the field, where we do these retrieval analyses of exoplanet atmosphere spectra, more often than not, the assumption is that the likelihood is Gaussian. But it turns out that actually when your data gets better and better, this goes in the wrong direction. Because as your error bars get better and you get more data points across the spectrum, correlated noise actually becomes more and more important. And the Gaussian assumption actually becomes lousier and lousier. So this motivates you to, at least motivates us to think about what this means, right? And I was also interested in the question, do you always need to write down a likelihood to do your analysis? Is the question I was interested in. And it turns out that the answer is no. And this is new to me. I'm still learning this. So I stumbled across this field and I picked up this textbook and started reading it. And it turns out there's a relatively new, I don't know what to call it. There's a new field, I guess, called approximate Bayesian computation. I'm not an expert in this at all, but we started picking this up because it's interesting. And this was invented by epidemiologists studying trends in human populations, where you couldn't write down a proper equation from first principles to describe human populations, much less write down a mathematical relationship explicitly for the likelihood. So these researchers were motivated by wanting to use Bayesian inference in an approximate way without having to either write down the likelihood or to compute it explicitly, right? So the likelihood is either intractable or cannot be written down. These kind of ABC methods are often described as likelihood-free, but this is not true. The likelihood-free just refers to the fact that you don't need to write it down, but the likelihood exists implicitly because the relationship, the mathematical relationship between your model data and noise exists whether you can write it down or not, and may be expressed semi-empirically, maybe expressed through a combination of theory and data. And the fundamental difference from standard Bayesian methods is that instead of maximizing the likelihood, you would like to minimize some abstract distance between the data and a suite of models, like, for example, a Euclidean distance. There are many types of distances you could pick, and this book talks about it in gory detail, subjected to some numerical tolerance. And there's a tension between making the tolerance too fine that you get Bayesian noise, versus if you make it too liberal, you get posteriors that are very far away from the true posteriors. So we were interested in this. And then we were also interested by the fact that a classical supervised machine learning method that's been known for decades seems to be a class of ABC methods, which I'll describe to you now. This is called the decision tree, right? So this is my cartoon attempt at describing a decision tree. So imagine you have a basket of fruit where you have a yellow banana, an apple, and a lemon. And now you would like to classify this fruit by asking questions. So you can ask questions like, is it sweet? Yes or no? Then that splits the lemon off. And you can ask, is it roughly spherical? And that splits the apple off from the banana. And the key point is that you can ask the questions in a different order, and you can ask different number of questions. And the optimal way to construct the tree is to ask questions in such a way that the information entropy is minimized. I don't have time to talk about this, sorry. And also you should be aware that, again, going back to the garbage in, garbage out rule, if you have something that's not in your training set, and then you ask the tree to answer that question, it will give you a ambiguous answer. For example, if you try to insert a green banana in this, and you ask about color, which was not in the training of the tree, probably doesn't give you an answer. So what does this have to do with interpreting spectra, you're wondering? So it turns out that when you interpret spectra, the conceptual structure of a decision tree is not very different. Because you're dealing with continuous quantities and not discrete quantities. This is now a regression tree. And now at the top, you would like to know the probability distribution of the parameter given the spectrum. I guess machine learning people call parameters labels and spectra features. So now you ask a slightly different question, but it's conceptually similar. You ask, is the ith data point higher than some threshold di? Yes or no? Then you split the spectra, the subset of spectra. And then you pick another point randomly and you say, is the jth data point higher than some other threshold? And again, you can ask these questions in different orders. You can play with your thresholds. You can play with the subset of data for which you're asking this question. And the whole point is that you would like to construct the tree in such a way that something analogous to information entropy is minimized. And if you're interested in this, there are two papers that taught me about this. One is a paper by Cremonesi et al. 2011 that talks in length about how regression trees sample the posterior distribution approximately. And then the textbook I just showed you claims that random foresters, which are ensembles of uncorrelated ensembles of regression trees, is a class of ABC method. So how does this look like in practice? Sorry, I have to show you this, but I keep forgetting the slides. So we published this idea in Nature Astronomy 2 years ago. And this was a really interesting collaboration between me and my PhD student, Chloe Fisher, who is in her last year, and two computer scientists who are working in biomedical engineering research, who apply machine learning to medical imaging and surgical tools. And the way to visualize it is to visualize each regression tree in the random forest as a voter. So now imagine you show one of these voters the spectrum in red, and you ask the voter, so what do you think the temperature and water abundance and the abundance of the other molecules are? Then given the training that you subjected the tree to, the tree will return an answer. And now you ask another tree the same question, and so on and so on. And now if you take care to ensure that the answers of the trees are not correlated, then you get these different answers that you can aggregate into approximate posteriors of the parameters. And in this paper, we demonstrated that getting posteriors in this way versus getting posteriors using nested sampling gave you roughly the same answer. But it gives you much more. In fact, one of the reasons we started using this method not because we could get posteriors, but because we were interested in the information content of spectra. So the JWST Cycle 1 deadline just passed a few days ago. For those of you who are working very hard for your proposals, you know this. And a key question on our minds when we propose for telescope time is, how do we optimize our use of the telescope time, right? And in the case of atmospheres, what wavelength should I look at with what resolution to detect the molecule I would like to detect? So with the random forest, you can run large suites of mock retrievals where you can give a synthetic spectrum to the forest, and you can test if they are giving you the correct answer. So you can test the real versus predicted abundance of a molecule, in this case, carbon monoxide. And you can show, for example, and this is not new knowledge, we just formalized this, that, for example, if you use a mode called G140M on using this instrument near spec on Webb, which has this wavelength range, it has essentially zero sensitivity to carbon monoxide. So if your scientific question is, what's the carbon to oxygen ratio of the atmosphere, you shouldn't use this mode, because you're going to be blind to a major carbon carrier. Instead, you should use this mode between 3 and 5 microns, because there are lines of this molecule in this wavelength range. And you can quantify how the predictability of each mode using a figure of merit called the coefficient of determination. You can also learn other interesting things. So if everything was perfect and ideal, you would naively expect that the real versus predicted would just march itself along this diagonal. There are two reasons why it doesn't. The first reason is because these models have noise in them. In fact, we inserted very realistic noise, and the noise produces this fuzziness. It also produces a minimum detectable abundance of each molecule, which you can predict using this method. The second reason why it's not a straight line through the diagonal is because of model degeneracies. So different combination of parameter values can give you exactly the same spectrum if you don't have enough resolution and coverage across wavelength. And also if your atmosphere is cloudy, cloudiness can also create a degeneracy. So this method captures also these physical degeneracies. The other thing that's interesting about the random forest method is that it answers the question, how important is each wavelength for constraining each parameter of the model? So all of these contributions in these plots must all add to 1. And they tell you the fractional importance of each wavelength point towards constraining, say, the temperature or the water abundance or the carbon monoxide abundance and so on. So using such an analysis, you can figure out which is the optimal mode to use for your Webb proposals, depending on what science question you're asking. If your science question is, what's the abundance of water, then you can just use another mode. You don't need to use this mode. You can, because water is present almost everywhere across the wavelength range. But if your science question is, what are the abundances of the carbon carriers, then some of these modes do not give you the correct answer. And you can ask the question using this kind of analysis. This is a summary plot of all of the different modes. Here's the translation of all. This is done by one of my second-year PhD students. And you can run all of these modes through this kind of analysis, and you can quantify this figure of merit. So 1 means you have perfect predictability on each parameter, and 0 means you have none. It never reaches 1 because of noise and degeneracies, as I just described to you. So you can use this kind of analysis to figure out what's the best mode you can use. And this is one of the reasons why we stuck to the random forest. I'm running, how much time do I have, Caro?
I think you have, I would say 10 more minutes, 5
okay.
to 10, yes.
Okay, so then I'll just cover this part. So I promise I'll talk to you about ground versus space-based spectroscopy. And the differences between the two are quite subtle. So when you measure spectra from the ground, you absolutely have superior spectral resolution by orders of magnitude. You can resolve individual spectral lines of atoms and molecules. But the price you pay for that is because you're observing through the Earth's atmosphere, you have a high level of noise. And I'll show you that traditional inversion methods do not work in this regime. And even worse than that is the fact that when you correct for the Earth's atmosphere, you do not have an absolute normalization on your high resolution spectra from the ground. And this loss of the empirical normalization, which is a different issue from the normalization degeneracy I talked to you about, leads to the fact that you cannot retrieve absolute chemical abundances. So for example, you can make statements like water is 5 times more abundant than methane, but you cannot make statements on individual abundances of water and methane. Space-based observations have lower spectral resolution, typically low enough that you do not resolve the individual lines of atoms and molecules. Rather, you resolve bandheads, you resolve the shapes of millions of lines being unresolved together. And here you have absolute normalization because you're in space, which means that your empirical normalization is absolute, and you can get absolute abundances, but you need to deal with the normalization degeneracy, as I just described to you. So if you're paying attention, the obvious answer is to combine the two approaches, right? You get the normalization from space, and you get the resolution from the ground. And indeed, sorry, I want to show you this slide. Indeed, there was a beautiful paper that showed this. I highly recommend reading this by Brogy and Line. And so this is from the ground, very high resolution, so high that you cannot really see the individual lines in this plot. And this is from Hubble, this is from space. And the clever thing in this paper was they realized that there's an analytical relationship between the cross-correlation function and the likelihood. And once you realize there's this relationship, that means that you can use traditional Bayesian methods to do the inference. And indeed, they can do this inference. And they prove that when you combine the high res and the low res, you get a better answer than if you just had high res or low res, not surprisingly. But the problem is that this method doesn't scale. This method doesn't scale because you have to flip the models in real time. And this spectrum only has 4,000 data points. And with 4,000 data points, it's already at the edge of what they can calculate in a reasonable amount of time. And now modern spectra, using modern spectrographs like Espresso, have 10 million data points. So you're missing at least 3 orders of magnitude, and this method does not scale. This slide shows you that the traditional methods by themselves do not work. And the reason is because this is the data, right? This is a simulation, this is the data in purple. And the noise on the data, which is empirically measured, is in gray. You can see that for each individual data point, the noise overwhelms the data. And so if you try to invert this spectrum point by point, you get back your priors, not surprisingly. This is the reason why people use cross-correlation, because cross-correlation leverages the information from many spectral lines to overcome this large noise. So now we have 2 problems I described to you, right? You cannot do the inversion point by point. And you would like to combine high and low res together. This I won't deal with in the next few slides. And you would like the method to scale to modern spectrographs. So how do we do this? And in the last few minutes, I will show you this solution. The solution goes back to thinking about something called feature engineering. So if you have a training set, in this case, we can only use models because we don't have empirical training sets of exoplanet atmospheres, unfortunately. But using a training set of models is conceptually identical to using a traditional Bayesian method with a quick model you can flip. You would like to extract the informative features from the training set using a machine learning model, and that gives you a train classifier. Deep learning does this step automatically. For example, convolutional neural networks, of which I'm not an expert. I mean, we run them and we get advice from our computer scientists. But as far as I can tell from reading the literature and talking to people, not only are neural networks expensive to run, they're actually not proven to formally compute posteriors. So it's a bit suspect to use them to compute posteriors. So what we do is we go back to the random forest and we do the feature engineering manually. And so we have a training set of models again, and we create cross-correlation templates of atoms or molecules that we want to detect in the atmosphere. We cross-correlate these templates with the grid of model spectra. And the big surprise here is not that you can do that. The big surprise here is that you can do that very sparsely and still get a meaningful constraint. In fact, you can do that sparsely enough that you can reduce the dimensionality of the problem, the number of points in the spectra, by 2 to 3 orders of magnitude. And if you work a little bit harder, you can get more. And you will train a random forest with a set of cross-correlation function sequences. I'm sorry, this is not very intuitive. But here's what a CCF sequence looks like. So these are cross-correlation functions at different combinations of parameters, very sparsely sampled. And the point is that at each combination of the two parameters, you get a function, not a number. You get a cross-correlation function that encodes information about properties of your atmosphere. And instead of dealing with 1 million data points, you have reduced the problem to a set of these functions, which you can then train your random forest with. And this actually works. So we tested this on synthetic spectra, but with empirical noise that we measured using a telescope. And we tested this against the so-called Bayesian neural network. There are probably more experts on the call than me who know about Bayesian neural networks, but from reading the original paper on Bayesian neural networks, I find it difficult to see why they are Bayesian. But in any case, they give you, in this example, the Bayesian neural network and the random forest gives you posteriors that seem reasonable and that seem centered on the truth, the answer you inserted into the simulation. But then at least in this version of the BNN that our computer scientists implemented, you can see that the Bayesian neural network seems to make certain assumptions on Gaussianity. And in this case, it really struggles when you have bimodal posteriors. We have good physical explanations for why we think the bimodal posteriors are real. You can read them in this paper if you're interested. So this is what we explored so far. And I guess I have run out of time, so I cannot tell you about this. But if there's 5 or 10 minutes at the end, I'm happy to talk about this too.
Thanks a lot, Kevin, for this very nice talk. So a comment to the audience now. If you have a question, please go to the participants and raise your hand. And actually, maybe one question from me regarding this big picture is do you think that in the future we can actually have complete characterizations of atmospheres in the sense that we can, no matter what molecules are present in an atmosphere, that we can have a full picture, that we can characterize an atmosphere of exoplanets? Or is it really, just individual molecules that we will be able to pick?
I think with the web spectra, you should get the dream, right? Which is already, people are trying to do this already with the past cycle. The dream is that you observe, you go on to observe a relatively large set of planets, maybe starting with the hot Jupiters and also the Neptunes. And in each one of them, you can overcome all of these obstacles with the inversion methods to extract the major carbon, nitrogen, and oxygen carriers. So this includes water, CO, CO2, methane, hydrogen cyanide, HCN, hydrocarbons like acetylene, C2H2, and so on, right? So I think there's every chance to do that. I think there's a very good chance that the community in 5 years, if Webb flies, will curate a chemical inventory, not just of Jupiters, but of Neptunes. In the part that I didn't talk about, I was going to argue to you that hot Jupiters are boring for Webb. It should do it very easily. And the frontier is not habitable super Earths. The frontier for Webb to do, in my field, are sub-Neptunes. These are the most interesting objects for which we will get a lot of interesting answers.
Thank you. There's a question from Lucio.
Yeah, so very nice, very, very interesting. Lots of progress. I was wondering, of course, there is the other level, which is the uncertainties in the radiative transfer modeling by itself. And can you comment a bit on what is the current state of the art?
So with the current Hubble data, that turns out not to be the limiting factor. And in fact, even with brown dwarf data, which has a resolution and quality approaching that of Webb, different groups using different radiative transfer method, like two-stream, what's the other one? The Fourier method, and so on. They get more or less the same answers. And it turns out that the thing that has a much bigger influence are the opacities, the cross-sections. The cross-sections have a much bigger influence on the final answer than the radiative transfer method. I think this may change when the data gets more and more detailed, but it's one of the reasons why so much investment in my community, at least, has been in the cross-sections.
Okay, could you use I mean, is there a way to understand better the differences between, the residual difference, even if they're small, between these different methods with machine learning?
I was hoping one of you could tell me that.
We can discuss later on lunch, maybe.
The problem with that is the challenge is that you don't have as far as I know, you don't have closed form solutions to test this on. You don't have closed form solutions that are not toy model enough that you can derive the posteriors exactly.
Yeah. So that how to estimate the error, essentially. Yeah.
So if you look in the literature, there are lots of arguments like my posterior is better than yours, but then my question is based on what?
Yeah.
Just because a posterior is skinnier doesn't mean the answer is better.
Yeah.
So, Caro, if you don't mind, there's I received the question directly in the chat.
Yes.
From Arnold Benz. So the question is, you find the water abundance of 10 to the -4 for hot Jupiters. This seems to be quite high and close to what it could be from cosmic abundance of oxygen. Please comment.
Yeah, this is a very interesting comment. Thanks, Arnold. There's several things to say. One is that the atmospheric abundance may not reflect the bulk abundance. So there may be processes in the atmosphere that actually act to enhance the gaseous chemistry, and this is not reflected in the bulk. This is a question that we are chasing, whether this is true. The second comment on that is that, you see, at the end of the day, these hot Jupiters are rather complex 3D objects. We don't know that for sure because we don't have a photograph of a hot Jupiter. But when you run realistic simulations in 3D, they don't look like 1D objects. And so when you try to interpret a 3D object with a 1D model, then you're taking some very crude average of, say, like the limbs at different locations. And recent studies have shown that this biases your answer. And so you can get artificially cold terminators. I don't remember what conclusions they drew on the water abundance, but I bet that if you get the temperature slightly wrong, you will get the abundance slightly wrong too. But the Hubble data is not currently good enough to answer this question. The web data will really pin this down. The web data, I believe, will not allow people to use simplistic 1D models anymore. You have to think a bit harder.
There's a question from Svetlana.
Yes, very nice talk, Helen, and lots of good results. So the question, I have one question and one comment. The question is towards this radiative transfer also that scattering has to be taken into account, especially for smaller mass planets, because the atmospheres, like Neptune's, they can get thicker and which can be further away from a star. So aerosols, it's really good conditions for forming aerosols, as we know, like this 1,000-degree range of temperature. How this is taken into account?
Thank you for raising this. This is actually very close to my heart. And when I raise this to other people in the field, I usually get ignored. Because the data is crude enough with Hubble that people get away with ridiculous assumptions like ignoring scattering or treating scattering in a very simplified manner. But one of the things that we think about in my group is the fact that there's a postdoc called Daniel Kitzman, and he looked at very influential studies on the early climate of Mars. There's a very famous paper in '97 by Forget and Pierre Humbert. They did some 1D climate simulations, and they showed that, look, if if you put in CO2 ice clouds and you tweak the properties of the clouds in a certain way, you can get scenarios in which the scattering of radiation by CO2 ice clouds results in a greenhouse effect. You scatter the radiation back to the planet, and Mars can have liquid water, right? And that paper has been cited like 500 times. Then Daniel came along and he showed that that was an artifact of the radiative transfer method. That was an artifact of not treating the scattering properly, as you were saying. And in fact, the method is called the two-stream radiative transfer. And the two-stream radiative transfer, I don't have time to explain, has this artifact of scattering too much radiation back, about 20% too much in one scattering. And
yeah,
so,
that is interesting because this is also used for Earth climate calculations.
yes, and the reason we thought I spent too much time thinking about that. The reason why it doesn't matter for Earth is because Earth's atmosphere is very specific. The water ice is very good at scattering optical and very lousy at scattering infrared. So when you apply the two-stream, even though there's an error, the error is very small. But CO2 ice is very good at scattering infrared. So if you apply the two-stream method in the infrared to Mars, you get a very large error. That's the reason. We spent like a year thinking about this. Then we fixed the method. We fixed the method.
Yeah, excellent example. Yes, and that's for exoplanets also could be important. Not for these hot Neptunes, but not ice, of course, but some other aerosols. Yeah, and as you found iron and Titan, then we can also talk about condensates of this. Yeah, and the comment I was, if I'm allowed for 1 minute, I was really interested to see your study on Bayesian likelihood and Bayesian methods and so on. I did this study like 1998, and I used non-Bayesian method, and I called it Occamian approach. So we use also Occam razor and not Gaussian likelihood, and used mean information in the data to evaluate the convergence of the result. So this kind of new ideas in those times, I see they slowly kind of entering the field. Something like would be interesting for exoplanets, to use it for exoplanets as well, for retrieval, because I use it for mapping stellar surfaces to get the star spots maps. Now I'm use this for mapping exoplanets from models, this 2019 paper, but it can be used also for retrievals as well, because this is a like inversion standard, inversion technique kind of. That
Could
you
we
have
send
data.
Please
The
send
reference, Berdugin 1998. I'm the single author there, so easy to find.
Okay.
Yeah, have a look. If you find it interesting, I can explain also details.
I would love to read the paper.
So maybe we have time for a few more questions, but I don't see any raised hands. So it's now the last chance if you have still a question. If not, I thank you. Judith has a question.
Yeah, I just wanted first the others to give room, because this is rather a philosophical question. Can we have like characteristic atmospheres, like we have characteristic planetary types? Can we have that, and whether they kind of correlate a little bit with the planetary types or where the planets were formed? So
that's the million-dollar question, isn't it? That's the question to answer. Again, I didn't have time to talk about this, but we argue, and not just we, but other people in the literature argue that one of the reasons why sub-Neptunes are more interesting is because there is indirect evidence that they are metal enriched, right? You see this in the solar system. And the papers, you should read the paper, if you're interested, you read the beautiful papers of Julie Moses, who talks about this. And she shows that for sub-Neptunes, if you can enhance the bulk metallicity and also the atmospheric metallicity by 2-3 orders of magnitude beyond solar, you start to get these very strange objects. You can get objects that are half CO2, half CO. You can get oxygen-dominated objects. You can get objects that have nitrogen, a bit of helium. So it's very difficult to answer that question. But we just wrote a web large program led by Marcus, where we argue that, we say that, look, you are in completely unexplored chemical territory. So the correct thing to do is to go out and look at a sample of sub-Neptunes and just look. You'll be surprised, right? Because you will find these strange non-solar system-like atmospheres. I don't know what they will tell you about formation. And maybe you will prove that it's very difficult to say something about formation, but I think we have to try before we give up.
Thank you.
Thanks a lot to everybody. I think I don't see any other raised hands. So Kevin, thanks a lot for this seminar. This was a very nice talk. There are, applause from everybody. And
thank you for 1 hour of your life.
Thank you.